So we're now going to be looking at chapter 11, where we're going to be looking at variable accelerations. In chapter 9, we were introduced to the Suvat equations, right? The 5 equations, which we should be comfortable with by now. But those equations only apply when the acceleration is constant. So remember, in the vertical motion, we had the acceleration as g, and the horizontal motion, we had this constant acceleration. And so if the acceleration is constant, then we can use those 5 equations. However, sometimes the acceleration may not be constant, in which case those equations will not apply, so we have to use a different method to describe the motion of a particular particle. So this chapter is going to be looking at when acceleration is not constant. So in this case, you can see here, we have a velocity against time graph. And as you can see, it's a curve, right? And we know from chapter 9, the gradient is just equal to the acceleration for a velocity time graph. So if this graph is curved, we know that therefore the acceleration is not going to be a constant, which means now we can't apply the Suvat equations, and so we're going to be differentiating and integrating. And so this is when we have a displacement or velocity, which is a function of time, meaning that the displacement and velocity equations have some t value in, meaning it changes with t. So let's look at a more simple question here. So we have a time t0, a toy car is at the point P. It moves in a straight line from point P and then returns to P. Its distance from P, s, meters at time t seconds, can be multiplied by this. So you can see here, s is a function of time because s is equal to 1/5 for t minus t squared, which means that as for different times, this s will change. So therefore, we have to work out the maximum displacement for part A. In order to do this, we're going to have to draw this graph. So let's just draw a graph. We know it's a quadratic graph and t will cross at 0 and 4 and will look something like this. Okay. Right, so this is going to be the answer for A. For B, the time taken for the car to return to P. So if the car is to return to P, S being the displacement will be equal to 0, right? So that's when in this graph here, we can look at when it crosses the T axis, so it's going to cross at T is 0. That's when this is starting. And when T is 4, so it's going to return when T is equal to 4. Right, the total distance traveled, well, it's going to travel the distance and then come back, right? That's what it says. So we need to work out the maximum S value here, i.e. the maximum displacement. This one occurs when T is 2, which I can plug into the equation for S. So S is going to be 1/5, 4 times 2 minus 2 squared, and it'll give us 8/5. So this is going to move a distance of 8/5 meters away and then come back 8/5. So the total distance will be this times 2, which is 16/5 meters. And finally, the values of t for which the model is valid. So as you can see here for the graph, I've drawn a graph out for all values of t, but it's only going to be applicable for when t is between 0 and 4, i.e. we don't want to include this part of the graph because remember S is displacement, right? It wants to, if it goes negative displacement, it means it's going backwards, and we don't really care about that because they said it's going to move forwards and then come back to its original position. Right, let's look at another one here. So a particle P moves on the x-axis at time t seconds. The velocity of P is v in the direction of x increasing. So as you can see, v is a function of time because it's got some t values inside here, right? Find the value when P is instantaneous at rest. So it's at rest when the velocity is going to be 0. So I can say v is equal to 0 and then solve for t. So we'll get 0 is equal to 1/5, 3t squared minus 10t plus 3, which I can now factorize. We'll get 0 is equal to 3t minus 1 and t minus 3. So therefore, t will be equal to 1/3 and t is equal to 3. So these are the two time values when the velocity is equal to 0. B, determine the greatest speed of P in the interval of between 0 and 3. So for later on, for this kind of question, we're going to be differentiating or integrating, but for now, because we don't really know the method for now, let's look about drawing the graph. So I'm going to draw this velocity graph, okay? So V against T. We know it crosses when T is 1/3 and when T is 3. It's a quadratic graph, so it's going to look something like this, and it's going to look something like this, okay? So this is going to be the graph. So ideally, we want to know where the maximum value of t or the v is going to be. So for this scenario here, when t is 0, you can plug it in. This will give you 3/5. And then we want to know when the maximum value of t is here. And this one here, if you were to work it out, it should be minus 16/15. So the greatest speed being the magnitude of the velocity, right? So it doesn't matter if it's positive or negative, we just care about the magnitude. The greatest speed will be equal to this 16/5 meters over 15 meters per second, like this. This type of question, as I said, we're going to look at later on in more detail to work out these values. All right, so as I said, the velocity, if the velocity is a function of time or the displacement is a function of time, then we can't use the Suvat equations, right? And so what we're going to be doing next is determining what to do. So in this case, what I'm going to do now is, remember the velocity time graph, the gradient is equal to acceleration, right? And acceleration is going to be the change in v over the change in t, right? Which I can next say is going to be dv by dt, because dv and dt just means the change in a small change in v over a small change in t. So therefore, I can say that acceleration is actually going to be the derivative of the velocity. Using the same method as displacement time graph, the gradient itself is going to be the velocity, which is a change in s over a change in t, which means I can say it's small ds over dt, a small change in s over a small change in t. That's why I get the velocity is the derivative of the displacement. So we've now learned two ways of determining the acceleration and the velocity from a velocity time graph or a displacement time graph. Using this, let's try and answer this question here. So a particle is moving in a straight line at time t seconds. Its displacement x from a fixed point is given like this. So x being the displacement is going to be equal to 2t cubed minus 8t. A, find the velocity of the particle when t is 3. So if we're given x, we know the velocity is just the derivative of the displacement, i.e. dx by dt. So I just have to differentiate its x function. This is 6t squared minus 8. And they're asking for when t is 3. So I just plug in 3 into this position here, and v, hopefully you will get an answer of 46 meters per second. B, the acceleration of the particle when t is 2. Right. We know the velocity, well the velocity is going to be equal to 6t squared minus 8 from part A, and the acceleration is the derivative of the velocity, i.e. we differentiate it once again, so it's going to be 12t, plugging in t is 2 into this equation here, and acceleration we get as 24 meters per second squared. So this just shows how we get the velocity and acceleration from a displacement function. Right, let's try another one. So a particle is moving in a straight line, at time t seconds its displacement x from a fixed point is given by this. So x is given by is equal to 4t cubed minus 39t squared plus 120t. Find the distance between 2 points when x is instantaneous at rest. So remember, at rest it means that the velocity is equal to 0. So we need to find the time when velocity is equal to 0. We have the displacement, so to find the velocity function, we just differentiate the displacement function with respect to t. So this will give me 12t squared minus 72t plus 120. I'm now going to equate this equal to 0, right? Because we want to find out when the velocity is equal to 0. This is going to give a quadratic equation which you will factorize, and hopefully you will get t is 5 over 2 and t is 4. So these are the two times where the velocity is going to be 0. Now the question is, find the distance between the 2 points where x is equal to 0. So when velocity is 0, where is the positioning? So I'm going to now replace these t values back into this x function, because that's going to tell us the displacement of the particle. If I do that, I will get that x is equal to 475 over 4, and x is equal to 112. And they want the difference between these two positions, so I just subtract them, okay? And you should get a value of 6.75. So this is just using the time values, or finding the time values from the velocity function and then inserting it back into the displacement function. Okay, so in the first part of the video, we looked at what's a maximum speed or a minimum speed, right? And we found that out by drawing a graph. But sometimes these graphs might not be too easy to draw. So in this certain cases, what we're going to do now is we're going to differentiate. So a particle, P, moves along the x-axis. Its velocity is given by this. Show that P never comes to rest. Remember, when it's at rest, the velocity is 0, right? So we have to just show that it's never going to be 0. You could do this by drawing this graph, this quadratic graph, or you can also do this by showing the discriminant, because the discriminant tells us how many roots there are going to be, right? So it just tells us how many times, or if there are any values when v is equal to 0. So the discriminant is b squared minus 4ac. B is minus 3 squared minus 4 times a is 2, c is 5, and we'll get a value of minus 31. This is less than 0, so it just tells us that there are no real roots, meaning there's no values or no values of t for when the velocity is equal to 0. B, find the minimum value velocity of P. So this is the case where we normally draw this graph and try and find the minimum V value, right? However, another way we can do it is, well, if it's a minimum value of V, it means that the derivative of the V is going to be to 0, i.e. the acceleration is going to be equal to 0. So what I can do now is I can say, if V is 2t squared minus 3t plus 5, I'm now going to find the acceleration function by differentiating the velocity function. This will give me 4t minus 3. And I'm going to equate this to 0, right? But if it's a minimum, it means the derivative, i.e. there's no more acceleration. If I solve for t will give me 3 over 4. So this is a time at which the velocity is minimum, which I can now substitute back into the velocity function. And I get that the minimum velocity is going to be equal to 3.875 meters per second, like so. Let's try a more difficult one. So we have a particle which starts at the origin. At time t seconds, we're given its displacement, its function of regarding time. So sketch a displacement time graph for the motion of p. First thing here, we have to just sketch this kind of graph. So it's going to look something like this. Remember, t is between 0 and 4.5, so we don't have to draw the whole graph. So it's going to look something like this, where we have s and we have time, like here. Hence, justify the restriction between 0 and 4.5. Well, this point here is actually going to be 4.5, and this is 0 here, right? So any values past that, i.e. here and here, we know it's going to be negative displacement, which we don't want. So that's why we have to restrict it between 0 and 4.5. Okay. B, C, hence find the maximum distance of the particle from O. So normally for the max distance, we'd have to find this point here, right? Let's call this X max. So we have to find the time at which is the maximum distance. Well, the maximum distance is when the velocity is going to be 0, right? I.e., you can see here that the gradient is going to be equal to 0. And if we were to differentiate this displacement, we'll get the velocity. So I can just equate that equal to 0. So first things first, if I were to differentiate this s, I'll get 9t minus 3t squared, make that equal to 0, and then I can solve for t. So t is going to be equal to 3. So that's the time when it's going to be equal to 0. So to find the maximum displacement, I replace it or substitute it back into the displacement function, and I get the s max is going to give me 13.5 meters. And lastly, D, find the magnitude of the acceleration of the particle at this point. Well, the velocity is 0 doesn't mean that the acceleration is going to be 0. So what I have to do is differentiate that velocity equation here. So velocity from earlier was 9t minus 3t squared. If I was to differentiate this to get the acceleration function, I'll get 9 minus 9t. And then if I was to now plug in t is equal to 3, right? Because I want the acceleration at this point into there, we'll get 9 minus 9 times 3 is 27, which will give me minus 18 meters per second squared, like this. So you can see here that we're just using differentiation to link between displacement, velocity, and acceleration.